what opportunities do you have in space exploration, in the space industry in general, as a physics graduate in particular? Since I'm also a physics graduate, and so I found that when I was working at a space company for a couple of years, I found the physics knowledge to be very useful. So, and then I started seeing a theme that, physics is multidimensional, and it sort of applies to many fields, including engineering fields. So space exploration is a very interesting area that way. Space exploration is, I think, as far as I know, there is no other field which has many intersecting elements from other fields as much as space exploration has. So I think space exploration is the most diverse field in that sense. It has, you require knowledge of physics, you require mechanical engineering, you require biology if you are sending astronauts or doing experiments with life forms or trying to find life on another planet. You require knowledge of chemistry and so many other things. So it's just really vast. uh, uh, Electronics and so on. So but even as a physics graduate, the subset of that larger requirement is still huge. And so the one of them is obviously rockets. So I don't know about you, but I love rockets. I think everyone does or should. Rockets are just amazing. They get you out of Earth's gravitational well, and that's just something to think about. It, achieving escape velocity is an interesting thing by itself. So there are various aspects to rockets where you can apply your knowledge to physics. One is, of course, laws of motion and predicting the trajectory of a rocket and engineering it to that effect. But there's also fluid mechanics, and that's one of the most complex things about a rocket. So simulating what comes out of these engines is insane. When I was at Team Indus, and we did not make rockets, we made spacecraft that went on the rocket. So this upper area that you see here, which is the payload fairing, what we call the payload fairing. So this here, this, so on. So our spacecraft or satellites sit inside this fairing, and but even they have small engines, right? So when I saw the propulsion engineers at the company modeling their engine, it was insane. Their simulations ran for hours, and they had to take into account all kinds of flows. They could no longer assume a pure laminar flow, for example, which is what physicists would like to do, because generalizing, smoothing, and all sorts of things. This was a real engine, so they had to account for all sorts of errors and real world things that would deviate from that ideal condition. So now if you take that and apply it to an entire rocket, it's insane. So you can apply your knowledge of fluid mechanics to understanding and making rocket engines and working for that. And I know that there are physics graduates working inside ISRO uh, on aspects like this. You can also make structures of the rocket which requires to carry, the rocket is going at some, at its peak it goes at about many rockets go at about 30,000 kilometers per hour or something of the sort. At the end of the day, you need to achieve orbit or escape, or have escape velocity if you want to have an interplanetary mission, for example. In that case, the stress buildup on the rocket, the mechanical stress is insane, the vibrations. So you need to model that vibration, and that requires a knowledge of the structure, what materials are being used, and so on. So that is also where your knowledge would be very you know appreciated. So in India, there is Hindustan Aeroliver Limited, and there's Godrej, and so on. There are other companies. These companies actually make the rockets for ISRO. So if you are, let's say, having a master's in physics, and if you demonstrate some sort of an engineering know-how, then it is very much possible that you can get a job at one of these companies working on rockets, right? And of course, these days, as I said, private space companies are not just limited to SpaceX in the US and companies like that. There are private companies in India which are up and coming and making their own rockets. So two of them, I've just listed two of them here, Agnikul and Skyroot. They are going to launch their rocket in the next few years. So before it's 2025, it is expected that they would have launched their first rocket in space. uh, so you could work for them as well. And of course, there are opportunities abroad, which is always the case. So that's one thing you could do. The other thing you could do is orbiters. So I think this is the most fun part personally. So Orbiters are most popular for sending to other planets and moons, where you want to send something to orbit an object for years and completely map it. And the instrument set on board that you have is very critical to select. So, for example, if you want to know if there is water on the moon, which is what Chandrayaan 1 discovered, how do you even decide what instruments you would put, right? So, as a physicist, you know how water ice behaves, you know the spectral signature of water ice, right? You know how, for example, if there is water in the form of hydroxyl versus water in the form of water ice, the signatures would be different. So you can tell that by your spectrometer. So you should know which spectrometer to pick. You should know which radar would work, to how much depth would it penetrate. So if there is water ice on the moon, you need to figure out what instruments would you build to find that out. And that's the job of the scientist, to determine how the engineer would build the instrument. So there are jobs available across the world, in space agencies across the world, where your scientific input and physics input is required to make instruments for spacecraft, right? And of course, not just other worlds, but also our own. There are thousands and thousands of satellites in Earth orbit and always growing. In fact, there are way more satellites in Earth orbit than any other orbiters across the entire solar system. So even there are many opportunities in terms of remote sensing, weather satellites, and so on. So there are many companies also in the space industry, again, both abroad as well as in India. So for India, there's Pixel Space and Dhruva Space, just to name a couple, who want your expertise in instrument building or deciding how the instrument would work. So that's another option. And then there's landers. So as I said, just yesterday, just 2 days ago, China landed a spacecraft on the moon, and they did it the third time. India was supposed to do this last year, but it unfortunately failed. Now India is going to try again next year, and so that's a great opportunity. Agencies worldwide again are sending landers all the time. So this is, here I have the Changi 4 lander, which China landed in 2018 on the moon. This is a real image, by the way, clicked by the rover, if you are wondering. So, and this is a concept image of the NASA InSight lander on Mars. So here are some instruments labeled. So it has, a seismometer. So if you are into that sort of, physics, where you could use a seismometer to figure out the interior structure of Mars, then you could do that. And there's a thermal probe here, and so on and so forth. So this is the seismometer, by the way. Here is the seismometer. This is the thermal probe, which is buried into the ground and trying to determine how much heat is coming to the probe, and using that to understand what is the interior structure of the planet, and so on. So landing missions are just being sent to the moon, Mars, and more worldwide. So you have opportunities there. And now there are private space companies trying to send moon landers as well. So one of them we already discussed, Team Indus, which was where I was working. And there are others outside, which is Astrobotic, Marston, iSpace, and more worldwide, which are doing more or less the same thing. Then there's rovers. I'm sure many of you are familiar with Curiosity. So this is a real picture of Curiosity taken using its own robotic arm. So it has a robotic arm which extends like this somewhere, like this, and it can turn the camera onto itself and click the picture and then use image processing to remove the arm so that it looks like someone has taken the picture of Curiosity. But anyway, so this is a real picture of the SUV-sized Curiosity rover that NASA put on Mars in 2012, and it is working to this day. And there are, apart from instruments which we already discussed, what we discussed for orbiters applies to rovers as well. You need to know which spectrometer to put on the rover so as to assess the rocks that it would come across in its journey, or the soil, what the soil is made up of, what is the composition, elemental composition of the rock, or the chemical composition of the rock. Both can be different things, by the way, depending on the use case, and so on. So that's one thing. But the other thing I want to highlight is these rovers are moving on a world which is not our own. Those are very harsh conditions. It's not Earth condition rover. It's not like driving a car on Earth. These are moving in very harsh conditions with rough terrains, blocky terrains, and temperatures which swing from very cold, -50 degrees, -100 degrees Celsius, to as hot as 200 degrees Celsius and everything in between. So rovers on the moon, Mars, and so on, they have to work in extreme conditions. So that requires you to have a knowledge of soil mechanics. For example, the soil on which your rover is going to move, it needs to have enough friction, right? So for example, on the moon, there is no water, at least not a lot of it. So it's not the kind of water content that we have on Earth. On Earth, the reason your car can still drive on a desert fairly easily is because the water is allowing for friction to be there between the wheels and the soil so that you can move on it. But on the moon, there's no friction because there's no water, and the particles are very fine grained, so your rover doesn't get the same traction. So you need to have, if this is your wheel, you need to have many grooves on your rover. So that's again where your physics knowledge comes in, of understanding of friction and all the coefficients related to that and so on. And you also need to understand the thermal environment that you are in and so on. So all of those things again are very well applied to space agencies as well as companies. So there are rovers dedicated to making, sorry, there are companies dedicated to making rovers. For example, uh, there's Cirrus Robotics, company dedicated to making planetary rovers. There's Astrobotic, who are building both landers and rovers. And there's a company called Honeybee Robotics, which is interesting. It doesn't make rovers, it doesn't make landers. What it does is it makes the drill that is on board these rovers, for example. So the robotic arm and the drill, it specializes in just that. So you can also work for companies which are contractors for companies which do space exploration. So it's a huge industry again. In space exploration, since you are sending spacecraft to other worlds, it has to travel through space, right? And it cannot travel through space in a straight line because that's just nonsense. So it has to use the laws of orbital mechanics. And that is where your physics knowledge is the most applicable directly in a real world setting. So for example, if you take the example of the Voyager spacecraft here, um, it used it is considered by many the best spacecraft mission from an orbital mechanics perspective, because what it did was it launched from Earth. Like here, if you see, what there were two Voyagers, twin Voyager spacecraft, Voyager 1 and 2. They launched from Earth within 15 days of each other. And let's just take any one Voyager. Let's say we take Voyager 1, okay, which is in white. So it launched from Earth in 1977. Then it reached Jupiter in 1979. It used the gravity of Jupiter. Basically, it went past Jupiter in a very close fashion, such that it could grab angular momentum from the planet and use it to speed itself to the next target, which was Saturn. Something as simple as exchange of angular momentum and the combination of orbital mechanics is used in this environment to go from Jupiter to Saturn in just 1 year, and then Saturn to Uranus, and then Uranus to Neptune. And these are huge distances, by the way. Neptune, for example, is 30 astronomical units away from the sun. And 1 astronomical unit is, of course, the distance between the Earth and the sun. So it's 30 times farther away than the Earth is to the sun, which itself is no very far away. So light takes 8 minutes. I mean, so these, by using clever use of physics and orbital mechanics, they they surveyed all the gas giant planets in just 12 years, and this was the first such grand tour, they called it. And they are on an escape route to the solar system because your velocity is so high. So on the right hand side you can see the orange part is the graph which shows at various distances from the sun, this is the velocity that you need to escape the sun's gravitational pull. So if you see, it launched from Earth. At launch, it had just enough escape velocity that it could escape the solar system. But as it started going away from the sun, the speed decreased because the gravitational pull of the sun was, the sun's gravity was pulling it away, making it slow. So its velocity started decreasing, but then it used Jupiter's gravity to increase its velocity again. And then so on with other planets. And, it's on an escape route from the solar system. So this is where your knowledge of orbital mechanics is super relevant. And not just this, but also for things like, for example, so there's a NASA mission called the Parker Solar Probe, where it is using the reverse thing of what Voyager did, where it is using the gravity of Venus to slow down and try to reach, tighten its orbit in a way that it can be within 5 million kilometers of the sun, which is where it wants to study the sun from, which is basically in the sun's atmosphere at this point. So it wants to study the solar plasma and try to understand why the corona of the sun is much hotter than the surface of the sun by being in the corona itself. And to do that, it is using orbital mechanics. So this is the trajectory: launches from Earth and tries to shorten its orbit by with every pass that it makes by Venus. So again, you could use that here, or you could, for example, use your knowledge of thermodynamics and make great insulators, because spacecraft are going to face conditions for, as harsh as minus 200 to 240 degrees Celsius, even worse in some cases minus 260 degrees Celsius uh, in space. So you need an insulating material which will protect your spacecraft and prevent heat from inside going out and the coldness from outside coming in. So that's also where you can apply that. And this is the New Horizon spacecraft. And this golden foil sort of a thing, it's actually not gold, it's insulating material. This is mylar and kapton, which is being, so this is a close up of it. You can see multiple layers of it. In between, there's nothing, because, you know, vacuum is the best insulator. So it is, the entire spacecraft is wrapped up in that, and all spacecraft are wrapped up in such material. And depending on your mission, the requirement varies. So which, as you know, because of your knowledge, you could apply that here. So that's one. Or if you are into, if you really dig how electromagnetic wave works, and if you dig working in communications, and if you don't work for someone like, let's say, Nokia, for building 5G networks or something of the sort, and you want to work in the space industry, the entire backbone of the space industry lies on infrastructure like having really, really huge antenna uh, positioned at multiple places on Earth in a way that no matter where a spacecraft is in the solar system, there will always be one part of Earth facing it where there would be an antenna, because the Earth rotates. So you need to have multiple antenna. So this is an antenna in, I believe, Australia. It is 70 meters wide, so it's huge. So for scale here, you can see some small sort of a house thing here, right? And there's lights here. So this is a huge antenna. This is used for communicating with spacecraft which are at very long distances. So for example, Voyager has, is more than twice as far away right now where Pluto is, and that's ridiculously far away. But this dish can communicate to that Voyager, and you can work out the math, because you know how much of a diameter of a dish would you need to be able to communicate to the spacecraft. So you could apply your knowledge here as well. And coming back to the Parker Solar Probe, apart from the orbital mechanics part, uh, you are trying to study the solar plasma here, and the radiation environment here is intense. So all your knowledge of, solar radiation, both in the terms of particles and, light, as well as cosmic radiation, anything that might still come across in that environment, plus plasma itself, the kind of temperatures that are involved, and all the coefficients that you must have, studied in the lab and measured it in your second year MSc. I remember measuring some of those coefficients. So all of this is applicable here, because you need to know that environment to be able to build the instruments in accordance with that, and measure things like the magnetic field, for example, local magnetic fields that are going on because of the charges flowing through the spacecraft, across the spacecraft, and so on. So you could do something like that. Or if you're completely not interested in pure physics and are into electronics, for example, and software, and have some physics knowledge as well, then you could write software for rockets and spacecraft and so on, or build the electronics that goes into these machines. So SpaceX famously lands its rockets, which is like just amazing. It runs like, this is multiple floors, stories high. It's a huge rocket. Here, the scale is not very apparent because there's nothing to compare to, but these are huge rockets, and it lands it autonomously, using multiple sensors and various sorts of things. So you could, build the avionics software, hardware related to this particular aspect of the mission. or you could build electronics for spacecraft, which is going to be in a very harsh radiation environment. So, for example, at Jupiter, where the radiation is intense, because Jupiter has the most intense magnetic field of all planets in the solar system, uh, only overthrown by the sun. So at Jupiter, the radiation is thousands of times more than what is faced by satellites in Earth orbit. So on the right side, if you can see, there's a box at the top of the picture. So that's a titanium shield within which all the electronics of the spacecraft are kept. And that is the thickness of the shield is calculated based on the radiation environment at Jupiter. So as a physics student, you are very well positioned to do that calculation and understand that environment. So this is another great example. By the way, I have an article on space grade electronics specifically, which I was talking about earlier. You should go and check that out. So with that, I come to the end of my talk. So the last thing is, please check out my blog. It's at jatan.space. So just go to your browser, enter jatan.space, and you will find articles on everything from the moon to planetary science to astrophysics to human space flight, to space missions and everything in between. And if you like my work, share it and support me. And